Orbital Assembly Corporation today had a very successful demonstration of our station truss assembly robot. We moved 6 tons of steel and built a football field length of truss in a record time, and this is going to allow us to build large structures in space, and we're very proud and excited of what our team accomplished today.
We'll be able to build many things, but one of the kinds of things we can build is space stations for tourism, for industry, and for research into a variety of things, such as the effects of the space environment on humans, partial G, all kinds of things that affect people when they're in space. We'll be able now to do that research and find out what do we have to do to make people thrive in space. Not just survive, but thrive.
I'm really excited about what we've demonstrated with the DSTAR, what this automated assembly technology can do. It's like if you're camping and you get out to the wilderness and you're setting up a tent and you've got this work you need to do as a human to put up this living space for you. And what we've demonstrated with this is this underpinning of a livable space. It's like bringing a pop-up tent with you to the campsite, and you press a button, boom, you've got your pop-up tent just ready to go, and your living space is there waiting for you. And that's what just really gets me excited about this, is that we're enabling this automated assembly of new territory in space that just gets you started and ready to go in bringing humanity out, above the surface of the planet.
Right here. I'm ready. Let's go. Let's go to space.
Well, our goal is to launch the P-STAR mission in 2023 and to build the gravity ring through that. From there, we're developing out the initial elements of Voyager space station, and our goal still is to spin up Voyager in 2027. We believe that the capabilities that we're iterating, the advanced manufacturing technologies that we're using, and the experience of this team can do that. And that's really exciting because that not only opens up Voyager Station, but that also opens up client contracts for space infrastructure like solar platforms, computing platforms, propellant depots, or of course more Voyager stations.
The way that humanity is advancing right now, we have to do these things in order to basically survive in the future. Because there's various calculations that you can do and figure out if we keep evolving as a population or keep having population expansion, the amount of energy that we use over time compounds and then we have to, we end up getting to a stage in 400 years where basically the whole Earth would have to be covered in solar panels, which is not possible. So we have to explore new ways and methodologies and how to live off Earth and to keep humanity surviving, because if we don't, we're going to run out of resources and things like that we have on Earth, be able to leverage the things that we've learned here and the people that are here and then start applying them off Earth. It's about the learnings and the understanding of things that we will enable in space. So once we start living in space, we learn a lot more about what's available and what resources are available, and then what we can or cannot use on Earth to keep Earth sustainable. I think that's the most important part. We simply don't know what we can use, and we can speculate, sure, but until we're actually physically doing it, just like we did it today, we have to make a hardware demonstration of the things that we want to do so people understand. And then the same application will happen when we use this technology and we create the station and then we live on it, and then we start to learn a whole bunch of things that we didn't understand before. And people understand, and it's a new advancement in everyday lives. And then can we apply some of those learnings back to Earth? I'm sure there'll be some applications, for sure.
And we are going to space.
What's the time?
Time flies in space.
What? Oh, no way! That's amazing. Yes. 30 seconds late.
Oh, okay. Wait. What was it? 20?
25-12, but let's say 24-24.
Oh my god. 24. Oh my god.
All right, cool.
Yeah. Oh my god.
24 minutes.
That's amazing. So,
you guys want to get in the line? You guys want to get in the line as before?
yeah, amazing. Good job.
So, well done. You guys get in the line, just like the bank. Photo op. Once again. Video.
So, guys, just a little bit of quiet. I'm sure some other people had some questions, right? Or I was the only one. So maybe Tim, just explain to us like that whole process. Like, how's that going to work in space? Like, obviously, what happens when you're not around? Like, just give us a bit of the overview of what they just saw.
Yeah, absolutely. So as I was saying, inside there's one little piece that's not automated, and that's the bolt driving. So we've designed a mechanism to take that part over, and our next rounds of funding will fund the development and the construction of those bolt driver boxes. So if you notice, the slowest part was Eric. It's true. When we can replace him with a machine, we're going to crush that 24-minute time. Okay. And in orbit, we can build straight trusses on orbit, and there's lots of applications for that. With our P-STAR mission in 2023, we're going to build a circular truss. So it's going to come all the way around and plug back into the backside of P-STAR. P-STAR will detach, and then we're going to spin up that truss with payloads on it and generate artificial gravity.
Wow, let's make some noise for that. Well, while we've got the whole team here, I'm sure there might be a couple of questions, obviously, because not everybody will be able to hear in one moment. Does anyone have any questions for the team?
And what are you the proudest of?
Gravity, hardest part.
Two answers to that. The hardest part was not building the truss. It was getting these things to keep gravity from clobbering us. When it came out, it wanted to go down. These things keep it from falling down. That turned out, because of the concrete sloping that way and sloping this way and being curved and so on, was actually more of a challenge than getting our machine to work. The proudest thing is showing that this team has come up with a method that can build big things in space.
Wow.
How does it feel for so many handsome guys work for a beautiful woman?
It's great.
I love working next to this handsome face.
Calm down, Jace.
I think there's another question over here.
Yeah. Do we have any other questions? Yeah. What's your name, man?
I noticed the whole system isn't particularly rigid. Will it be hard to match up the two ends when it gets to the circular form?
Yeah, so one of the things so the question was, he noticed that the system wasn't entirely rigid and it will be hard for that to match up.
Right.
So it's not entirely rigid because of budget cuts. So most of the DSTAR, the initial funding and fabrication was funded by the founders. And so we were operating on a very limited budget in order to get the demonstration done. If you notice, there's these cross frames are every other segment. And so those are the weak points where we didn't have those cross frames. So when we go to P-STAR and on orbit and we're building Voyager Station, we'll have all of those intermediate frames in place, and then that'll increase the rigidity. Did you want to add anything to that, Tom?
Yeah, as far as putting it out of the what we call the P-STAR in orbit, when that comes around, you can't be guaranteed it's going to be perfectly aligned to come in. So we're building into the joints a little bit of flexibility, so when it comes around to the end here, we can guide it in. There's enough flexibility to guide it in and mate the front end with the rear end and have a complete circle.
So what kind of fairing, what were you looking at to get this in orbit? You know, is this about the size of the unit that's going to orbit? Is it just a smaller unit? So, you know, fairing size and everything. I assume your size is massive.
Yeah, no, that's
the first orbital system is going to be quite a bit smaller than this. This one, it's 2 meters, about 6'6", 6'7", across and vertical on the inside. We're going to be something like half a meter, or on the order of what, 20 inches on the inside. So it'll be much smaller. We can fit the whole thing into existing fairings.
So you know, something like a Falcon 9 or even something on that size.
Yeah. So Tom brought up a good point there. So D-STAR here is 2 meters by 2 meters. You can walk through it. The gravity ring will be 1/4 this size, half meter by half meter. Voyager Station will be almost twice this size, and we have a tape outline on the pavement behind you of the center of a Voyager Station module, if you want to check it out. That's where we're headed. And to get the truss, the STAR, the full-size truss for Voyager Station, we'll need heavy lift capabilities. Yeah.
How will you take it out of SpaceX rocket? Because I understand you are choosing SpaceX to take it into space. And how will it look like to put it out there?
But we're evaluating several different launch companies. We want to make sure that it fits comfortably in a fairing. We haven't picked who our launch company is yet, but that's up for discussion.
And will you use astronauts in some part of the process? Because I know your goal is not to have humans assemble it in space, but do you plan to have astronauts present as a part of your mission?
Not in our first mission, no.
What other questions, guys?
And a follow-up to her question, how do I sign up to become one of those outfitters?
You're here, you're on the books.
I'll work for free.
Signed up.
All right.
Sweat equity right there.